So, welcome back. Let's do Ampere's law. So, okay, Boyer-Savat's law is great under some circumstances, but for some things it's not so easy to do. Even a long straight wire is not so easy to do because R changes. If I have a piece of wire like that and I just want to know there's my point of interest. If I take my DS's, if I take my DS and my R hat, well, the problem is that the R hats have different relationships to the DS's and the R's are different. So everything's going to be different. So it's going to be a real pain doing it. It's doable, but it's going to be a pain. So, okay, is there an easier way? And probably this is why we don't do the more complicated problems using Boyer-Savat, because it's kind of like, we've got an alternative that works sometimes. And that is basically we have a thing called Ampere's law. And basically what's going on here is, okay, I have a current carrying wire. Let's have the wire coming towards me with the current coming towards me. And it's going to make a whole bunch of, I can draw these magnetic field lines as concentric rings, can't I? I know it seems a bit weird that they don't start and end anywhere, but that's magnetic field lines. When I have a bar magnet, the actual field lines go in a ring. They don't stop at the surface of the magnet. They kind of go in rings. Well, the same thing's happening here. These things go in rings, and it turns out that with the right-hand rule, if the current's coming towards me, then these guys are going to be like that. So the B is going to get, if you had a B direction finder, it would follow that circle, and another B direction finder would follow that, like the tree, like the rings of a tree. What's your gut feeling? What's your engineering intuition tell you? Would the B be stronger on this bottom ring or inside ring as compared with the outside ring? What do you think? Which would be the strongest magnetic field? So the one, if you had a magnetic field meter, if you put your magnetic field meter on this bottom ring where the arrowhead is, or you put it further away from the wire, which would be the stronger magnetic field? Closer, because if it's stronger further away, then I must get overwhelmed by magnetic fields from Pluto. Again, things can't get stronger as they go further away, or else stuff across the universe will kill us. So it must be falling off. The influence has got to fall off. So yeah, the B's going to get less and less and less as I go further away. So B is falling off. Is anything increasing? Yeah, my length of not my wire, got to be careful here about what I'm looking at. DS, we talked about before, was the little bit of wire with the current flowing through it. Now, I'm going to talk about my DS is going to be my little bit of imaginary magnetic field line. And it'd be nice if we called it something else like, D imaginary field line, so there wasn't any confusion, but, after a while we'd all be writing down DS and, It's only confusing when you're new. Once you've been in it, it's not confusing anymore. So the textbooks are written by people who've been in it a long time, so they don't even think about, I just use DS for the length of wire, and now I'm using DS for a magnetic field line that's going round a piece of wire. So you got to be. I got a shock when I did my master's degree. It's the first time. So in Britain they have, and it's a real shame. If I could change anything about the United States, I would install morning coffee and afternoon tea. I've not looked at anywhere that has it. And man, it is one of the inefficiencies of the United States. Because in my department, at 10:30, everybody would stop for 15 minutes and have coffee together. And at 2:30, everybody would stop for 15 minutes and have tea in the afternoon. And it seems like that's inefficient because people are going to not make that phone call now or whatever. But what it does is, twice a day, you'll be in a room with everybody in your division. So I need to talk to you. I'm going to talk to you at tea. I don't need to chase you down. I just go on up and I go and talk to him. And we have this little conversation while we're having a cup of coffee or a cup of tea. It's incredibly efficient. And, I want to lead by example or chat to people or encourage or whatever. It's a brilliant time to do it. And when you're undergraduate, you're not part of a group, so you don't get to go to tea with anybody because, you're not part of that division. But when you become a graduate student, you're part of a division. So then everybody puts down their tools and goes off to morning coffee. And you go, okay, so I go off to morning coffee. And you find your supervisors there going, how are things going and what's going on? And it's like twice a day, this exchange. And I want my supervisor to sign a form so I can get some supplies. He's there. I know where he's going to be. So it's brilliant. And so why was I telling you all that? There was a reason why I was telling you all that. That was really to do with the lesson in hand. And let's have a look. We're talking about Ampere's law. We're talking about the, oh yes. Oh, yes. So I got a shock because I got through my undergraduate degree. I wasn't brilliant by any means, was average. Did just well enough that I could stay on for the master's degree. The guy that became my master's supervisor was an undergraduate teacher of mine, took me for one course, which I loved. And he'd interviewed me to get into the university in the first place. So there was a bit of history there. But, frankly, I was very grateful to be in his group. And he was just talking. He was only 10 years older than me, which when I was 21 seemed like a lot, but now I'm 63, doesn't seem like so much. Also, I'm sure I'd still be deferential if I saw him. It'd be like the old behavior pattern would still be there. And he's talking about when he was an undergraduate. And he said, I spent most of my time as an undergraduate rewriting my notes. So this was before notes were produced and all that kind of stuff. And we'd all sit at the back and scribble like crazy, And I said, what? And he said, yeah, you get your notes that you take in the lecture, and then you get the textbook, and you rewrite the notes properly, looking at the textbook. Just making sure that there's no slips in the notes. And I'm going, slips in the notes? And he goes, yeah, professors, they always give the drop a square and all that. And I remember going on for hours, where did that square go? And why did it disappear? And I'm just going to have to remember that square disappears. When it doesn't disappear, it was just the faculty member dropped it and just went on with the derivation. And it's like, it just never occurred to me the fact that they could make a mistake. That was one thing. But secondly, it never occurred to me that I should rewrite my notes and double check and all this kind of stuff. And he said, well, when else do you learn to do this stuff? It's by going through that you learn to do this stuff. And you put it all together. And I think that stuff like that stuff about DS being used for different things at different times, if you just look casually, it's totally confusing because the same letter has been used sometimes for a current in a wire, sometimes for this a length on a imaginary field, and you don't spot it. It's just DS, and DS is DS is DS. But if you live with it for a while, then stuff like that becomes more obvious. So I do think, I don't have you, my wife actually has suggested a few times, just get rid of all notes. Just have people do it traditional way and write stuff down, and then have them rewrite the notes, and then have them show you the rewritten notes, and make that an assignment. And I ain't going to do it. But there's some way, you need to find some way of living with these materials and thinking about it. And the homework helps. It helps divide it. But if you want to go to that next level, that's part of it is just looking at stuff like that and just spotting those things. Okay? So anyway. So, yeah, Ampere's thinking, oh, yeah, look, my magnetic field's decreasing. as the length of the circumference increases, I wonder if they balance each other out. Is there a consistency there? And when they did the measurement, sure enough, there was. We like equations, which are balances. So what he found is that as my magnetic field falls off with distance, so my circumference increases with difference. I better draw it the right way. Anyway. And so we always get this constant value. So we can say, consider a magnetic field around a long straight current carrying wire. As we move further away from B, the wire B decreases, but the circumference of the circle increases. Is something conserved? The line integral of B dot ds, let's be professional about this, have little things on top, and around any closed path equals a constant, mu naught I. I is a constant for this particular piece of wire on this particular time, where I is the total continuous current passing through any surface bounded by the closed path. So we have the line integral of B dot ds is equal to mu naught times I, and that's Ampere's law. So just like you know Boyer-Savat's law, know that law. And so here's an example. So let's take that example, which would have been quite hard using Boyer-Savat, and now let's do it using Ampere's law. An infinitely long current carrying wire follows the positive y-axis, so it's pointing upwards on my page. Use the method of Ampere's law as shown in class to show that B is equal to mu naught I over 2 pi r at the point that is r meters from the wire. So here's my diagram. I have my r meters. There's my point of interest. I did my little imaginary. I tend to do my imaginary lines as dotted. Gauss's law, I did my Gauss's surface as a dotted line, or a different color, but you've got to somehow make it stand out. And there's my wire, and there's my little ds, and etc. And I say, let's have a look. The line integral of B dot ds is equal to mu naught times I. B is parallel to ds. If you think about it, if I'm drawing this and my current is coming out, then what I do is I have a whole bunch of, so my B would be like that. And I am drawing my ds in the same vein. They're both tangential. So B is parallel to ds. It's got to be, And then I decided to make my imaginary, so now I've got to be, so got to stop another little bit. I need to change color pens, because let's be really clear about this. So the red is the wire with the current coming out, and the red is the magnetic field that's caused by that wire. Agreed? Now, I am choosing to do a closed loop which is also circular. I am choosing to do that. I am choosing, because I'm smart, because I know what I'm doing. And I am choosing, therefore, to put my ds parallel to B. In truth, I could be kind of slack, and I could say, well, okay, I don't know what to do with my Gaussian surface, my Ampere's loop. I'm going to make it like that. And there's my ds. And that does not hold, because I chose to use a really wacky Ampere's loop. So just like I was careful about how I drew my Gaussian surfaces, now I've got to be careful about how I draw my Ampere's loop, because I decide that. So this bit in red here is done by me. I chose to do it. Yeah, the magnetic field is circular, so I picked a smart choice, but it was my choice. So for my choice, B is parallel to ds. And B is constant because, well, B is constant along my loop because I made my loop equidistant. So I picked a really good loop. So B is constant. So that means B can come out of my integral. So it's B, and also I skipped a step there, didn't I? B dot ds is equal to B times ds times the cosine of the angle between. And because these two guys are parallel, that's the cosine of 0, which is 1. And so I then get the integral, I then get that integral without the dot. And then I can say, well, my b is constant, so the b comes out. Integral ds, line integral ds equals mu naught I. And my line integral ds is going to be, well, I did a circle, didn't I? I chose to do a circle. So that means that's 2 pi I. Not 2 pi I because the magnetic field forms a circle, but 2 pi R because I drew my Ampere's loop as a circle. And so I get that. And so I go rearrange, b equals mu naught I over 2 pi R. Boom. Done. So a lot easier than trying to use Boyer-Savart for that. That's nice. Using the method of Ampere's law shown in class, determine the magnitude of the magnetic field at 0.7 meters from an infinite long wire. 5 amps. Creates a magnetic field. Not drawn very well. There's my B. That there will make 7 meters. I choose to draw a Gauss's, I try to do an Ampere's loop, and I'm going to make my Ampere's loop go through the point of interest, as we always do, of course, no point in doing it anywhere else, and also be nice and symmetrical, which means it's going to be circular. My choice. My ds is therefore parallel to my B. I come along and I say Ampere's law, the integral of B dotted with ds is equal to mu naught times I. Agreed? So in this case we have B is parallel to ds. So B dotted with ds, which equals B times ds times the cosine of the angle between. That angle is 0, which equals B times ds times 1, because cosine of 0 is 1. Oh, so this means that the integral of B dot ds can equal the integral of B ds. I know it doesn't sound like much of a change, but it is, which equals mu naught times I. And then B is constant on my Ampere's loop. So the integral of B dotted with ds equals B times the integral of ds, which equals mu naught times I. And the integral of ds is equal to 2 pi times r. So B times 2 pi times r is equal to mu naught times I. So B is equal to mu naught I over 2 pi r. So B is equal to mu naught, and I was 5, and 2 pi, and r is 7. So this equals 5 over 14 pi mu naught Tesla. Yep. Cool. Cool. So, let's make it a bit more interesting. So now we have a helix of wire. This is what you're going to do in lab today, actually. We have a helix of wire. So it's going round and round and round and round, like what's that ride at Busch Gardens that does a helix? Is it? It's not a She-Crit, it's the one that goes like a corkscrew. Montu?
Yellow one?
Yeah, the yellow one. Okay, so it's like Montu. It's like a corkscrew. It goes round and round. I want to find the magnetic field inside it. That's where all the magnetic field is. The way this works is, if that's my corkscrew, it's got a strong magnetic field inside. And there's actually very weak magnetic fields on the outside because it's, you know, very widely spaced and all that. So the magnetic field is all pretty much down the middle. I'm looking at it. I've cut it in two. I'm looking at it. You know, there's the front, there's the back, and I'm going to use a Gaussian, a Ampere's loop, which is not circular. But I'm going to do the same thing I did with Gauss's law. I'm going to pick bits of this loop that are to my advantage. If I can, I'm going to get my ds and my b to be parallel or perpendicular, not in between. And if I can, I'm going to have bits where there's no magnetic field, or there is the magnetic field, but not in between. So as it turns out, and this is one of the issues we kind of like, if you were working this out for first principles, having never seen it before, it'd be a real tour de force, but we've all seen it before, so it's a bit like memorization. It's not so bad if you think about the logic of it. I'm going to draw a rectangular loop. This is the imaginary Ampere's loop. I'm drawing a rectangular Ampere's loop. There's 4 bits to it. 1, 3, 2, and 4. 1 and 3 kind of look the same. So I'm going to take my, let's do this in red so that I don't. So can you see I'm making my little ds there, and there's my magnetic field. And can you see how the magnetic field and the ds are perpendicular to each other? It's a dot product. Dot product for 90 degrees, cosine of 90 equals what, 0? Oh, so because I picked the top and the bottom at 90 degrees to the magnetic field, for side 1 and side 3, B is perpendicular to ds, so B dot ds equals 0. So forget about them. Not going to have any effect. So that's those two taken care of. And then the other kind of cunning thing I did was, so there's my ds there. Then the other cunning thing I did was, yeah, on the outside, my ds is in line with my b, but b is so small it's not even worth thinking about. So outside on line 2, b is effectively 0, so forget about that as well. So that just leaves this inside bit. And on this inside bit, my ds is parallel to b, so I'm going to say the integral of b dot ds is equal to mu naught times I, and b is constant because it's a solenoid and we know that it's constant, so that can, and also what I should have said, so I should have said, of course, I skipped that step, shame on me. I said ds is perpendicular to b, so b dot ds is equal to the magnitude of b times the magnitude of ds. Because down here, I'm kind of doing it, you know. So then I say, well, b is constant, so I can say that should be there as well. So I can say, well, line integral ds is equal to mu naught times I. And then I go, well, my line integral ds is simply, well, it's just the length inside of my loop, which I made up. I'm going to call it L dash, because it's not the same as the length of the solenoid. It could have been, but I chose to not make it that way. So the line integral of ds for this side 4 is equal to L dash. So B times L dash is equal to mu naught times I. But what current is flowing through my loop? Well, it's I, but it's 1, 2, 3, 4, 5, 6. It's so many turns. I goes through once and goes through again and goes through again. So my current is equal to I times the number of turns inside my loop. It's not for the entire coil, it's just the number of turns inside my loop, which is N dash. So I get B L dash is equal to mu naught I times N dash. And then I have a little bit of an insight, and I go, because it's a nice uniform coil, then I can say the number of turns in the little bit of length is the same as the number of turns in the overall length. So N dash over L dash is equal to N over L, which is what I was given. N and L. So B is equal to mu naught I N over L. Boom. I got it. How are we doing for time? I'm going to just let that go. Okay? I don't have time to go over it again. Actually, I am going to do it. Okay? So let's do it. Solenoid wire has a radius of 3 meters, 6 meters long. Consists of 10 loops. N is equal to 10 loops. Current I is equal to 8 amps. Using the appropriate equation. Oh! Not using Ampere's law. So let's just do it using the appropriate equation to begin with. So B is equal to, what was it? Mu naught I N over L. That it? Yeah. Let's have a look. I got my currents in there. I got the number of turns per unit length. Yeah, I think that was it. Yeah, let's go back and just double check. Mu naught I N over L. Think about it. It's mu naught times I scaled by the number of turns per unit length. So this would equal mu naught times 8 times N. Well, N was 10 over L. L is 6. So that would be 80 over 6 mu naught Tesla. Not bad. Let's say we wanted to do it using Ampere's law. Put down your law. You know, B dotted with, what is it? B dot mu naught times I. Mu naught B dot ds, integral B dot ds is equal to mu naught times I. For 1 and 2. B is perpendicular to ds, so integral B dot ds equals 0. That's B. For 3, B is 0, so integral B dot ds is equal to 0. For side 4, B dot ds is equal to mu naught times I. B is parallel to ds, so B dot ds equals B times ds times the cosine of 0, which equals 1. And b is constant. So b dot ds, which equals b times ds, the integral of b dot ds, which equals the integral of b times ds, which equals b times the integral ds, is equal to mu naught times I. Integral ds is equal to L. Let's just put L dash, L dash. I is equal to, I dash is equal to n times I, n dash times I. So we get that b times integral ds, L dash, is equal to mu naught times I. So b is equal to mu naught I over L dash. And I can say that b is equal to mu naught. And my current is equal to n dash I over my length is equal to L dash. And then recognize that n dash over L dash is the same as the total number of turns over the total length, which gives me that b is equal to mu naught ni times n over L, which equals 80 over 6 mu naught Tesla. So, yeah, not that bad. Okay, I'm going to stop recording.